Travel back 12 billion years to a universe still raw and young, and place yourself at what should be a safe distance from a single point of light. There is no safe distance. What burns in front of you is a disk of gas wider than our entire solar system, spiraling inward, torn apart and heated until it outshines a galaxy. At its center sits a black hole, and it is eating, not slowly. Not at the careful pace the laws of physics are supposed to enforce. It is swallowing matter at a rate that should tear its own meal away from it, and as it feeds, it shrieks in X-rays and launches a jet of charged particles thousands of light years out into the dark. Every model we have says this cannot be happening. A black hole feeding this hard is supposed to choke itself silent. This one isn't choking, it's accelerating, and it's breaking not one law but two. To understand why that's frightening, forget the idea that black holes simply suck things in. They don't. They feed, and feeding is a messy, self-limiting process. Gas falling toward a black hole doesn't drop straight in. It piles into a flat, whirling disk, and as it grinds inward, it heats to millions of degrees and blazes with radiation. Here's the catch. That radiation pushes back. Light itself carries pressure, and the brighter the disk burns, the harder it shoves the incoming gas away from the mouth of the black hole. So there's a natural ceiling. Feed too fast, and the black hole's own brilliance blows its food supply outward before it can fall in. The point where the outward shove of light exactly balances the inward pull of gravity has a name. It's called the Eddington limit. Think of it as a cosmic speed limit on how fast any black hole can grow. Cross it, and the black hole should starve itself. The object we're looking at is feeding at 13 times that limit. For decades, the Eddington limit was treated as close to sacred. It set the schedule for the entire life of a black hole. Feed, brighten, push your own fuel away, settle down, wait, feed again, steady, capped, predictable. That schedule had one uncomfortable consequence, which we'll come back to. On a strict Eddington diet, it takes an enormous amount of time to build a truly massive black hole. Time the early universe didn't have much of. For years, astronomers filed that tension away as a problem for later. Then a quasar from the young universe showed up and tore the speed limit to shreds. The find came from a team led by Sakiko Obuchi at Waseda University, working with researchers at Tohoku University. Their tools were a pair of unglamorous workhorses, not Webb. They used the Subaru telescope in Hawaii to read the motion of gas swirling around a distant quasar, which let them weigh the black hole at its heart. And they combined that with X-ray data from a wide sky survey to clock how fast it was feeding. The quasar's light had traveled about 12 billion years to reach them, from a time when the universe was less than 2 billion years old. When they ran the numbers, the feeding rate came back at roughly 13 times the Eddington limit. They checked it against the radiation it was throwing off, and it held. The object carries the survey tag ID 830, and the deeper they looked, the less sense it made. 13 times the limit is easy to say and hard to feel, so anchor it to something with a red line. Picture an engine. Every engine has a maximum safe speed, a point past which it shakes itself apart. The Eddington limit is a black hole's red line. Run an engine slightly over its red line and it screams. Push it far past and it destroys itself in seconds. This black hole isn't sitting just over the red line. It's pinned at 13 times past it. And instead of tearing itself apart, it keeps running, hotter and faster, dragging in more matter than its own light should ever permit. It's the equivalent of flooring an engine to 13 times its breaking point and watching it run smoother for it. That should not be possible. The contradictions only stacked higher. First, the speed itself. 13 times the Eddington limit isn't a small overshoot you can wave away as measurement error. It is a black hole doing the one thing the physics of accretion is built to prevent. Second, and stranger, it's doing two incompatible things at once. It's blazing in X-rays, the signature of gas being violently devoured right at the edge, but it's also firing a powerful radio jet, the signature of a very different kind of system. Most models say a black hole should be doing one or the other, not both, not simultaneously. This one is. Third, and this is the part that should unsettle you most. What we're seeing is almost certainly a snapshot of something fleeting, a phase this extreme can't last long. We didn't catch a stable monster. We caught a single frozen frame of something mid-frenzy, billions of years ago, which raises an obvious, uncomfortable question. What were we lucky enough to witness? The team's answer is that we caught it in the middle of a binge. Their leading explanation is that this black hole is passing through a brief, violent, transitional stage, where a sudden flood of gas dumped onto it all at once and overwhelmed every break the system has. For a short window, the normal rules break down. The black hole feeds far past its limit, lights up in X-rays, and fires off a jet all at the same time before the frenzy burns out and the system settles back toward something ordinary. What could trigger a flood like that? One real possibility is grim. The black hole may have shredded and swallowed something whole, a star or a dense clump of gas that wandered too close and was torn apart, force-feeding the monster in a single catastrophic gulp. So this isn't a steadily growing giant. It's a black hole caught in the act of gorging itself, and that connects directly to one of the deepest unsolved problems in all of astronomy. At the center of nearly every large galaxy, including our own, sits a supermassive black hole, weighing millions to billions of times the mass of the Sun. They are the anchors of the cosmos, and we have never fully explained how they got so heavy. Because here's the problem we set aside earlier. When astronomers find these giants in the early universe, they're already enormous, fully grown monsters existing when the cosmos was barely out of its infancy. On a polite, speed-limited diet, there simply wasn't enough time for them to bulk up that fast. Something let them cheat. Something let them grow faster than the rules allow. A black hole like ID 830, caught flagrantly shattering the speed limit, is direct evidence that the cheat is real. The only question is how far it goes. Because ID 830 isn't an isolated freak, it's the newest entry in a growing catalog of early universe black holes that look too big, too fast, too soon. Telescope after telescope keeps pulling them out of the deep sky, and each one sharpens the same suspicion. The growth limit we treated as a hard ceiling may be broken far more often than we assumed. It would be dramatic to say physics is wrong. It isn't. The Eddington limit is real, and most black holes obey it. What's becoming clear is that our picture was incomplete. We learned the rule before we had instruments powerful enough to catch the exceptions. Now we can catch them, and the exceptions are pointing at something we genuinely don't understand yet. Which leads to a question even stranger than a black hole that eats too fast. Breaking the speed limit only helps if you already have something to grow. A black hole can't binge its way to billions of solar masses from nothing. It needs a starting point. A seed. So where did the seed come from? For a long time, the assumed answer was that every black hole begins as a dead star. A massive star runs out of fuel, collapses, and leaves behind a black hole a few times heavier than the Sun. A small seed. Then it spends eons feeding its way upward. But run the math on that, even with occasional binges, and for the very biggest early monsters, it's a desperate stretch. The seed is just too small, and the clock too short. So theorists propose something far stranger. What if some black holes never were stars at all? The idea is called direct collapse. In the early universe, under just the right conditions, an enormous cloud of pristine gas could collapse in on itself so smoothly that it skips the star stage entirely, folding directly into a black hole tens of thousands of times the mass of the Sun in one stroke. Not the corpse of a star, a black hole born huge, from gas alone, a heavy seed, with a colossal head start. And this is where the two ideas lock together into something genuinely unnerving. Start with a heavy seed, a black hole already born tens of thousands of solar masses from a collapsing gas cloud. Then let it occasionally feast far past its speed limit, exactly the rule-breaking behavior we're watching ID 830 do right now. Combine a giant head start with permission to binge, and suddenly the impossible timeline closes. You can build a billion solar mass monster in the narrow window the early universe allows. The direct collapse idea was developed by theorists including Mitchell Begelman and Martin Rees in the mid-2000s, and it remains one of the leading explanations for the early giants. What's changed is that ID 830 hands us the missing half of the picture. It's real, observed proof that black holes can shatter their growth limit. The binge isn't just theory anymore. We may be watching one of the mechanisms that built the monsters at the hearts of galaxies. None of this is settled. We still don't know whether the early giants grew from heavy seeds, light seeds, or some mix. And ID 830 is a single snapshot of a single object, not a final verdict. The Super Eddington explanation is the best fit the team has, but the strange pairing of X-rays and a radio jet means there's clearly more going on than we fully grasp. More observations are coming. Both answers would be extraordinary. A few years ago, the way black holes grow felt like settled textbook physics. Now there's an object in the early universe feeding at 13 times the supposed limit, and a serious case that the giants anchoring every galaxy were born in violence we're only beginning to reconstruct. Even the monster at the center of our own galaxy grew up somehow. So what do you think built them? Tell me below. And if this is your kind of question, subscribe.